Thanks for having me. If you guys want to follow along, I'm sorry for this, but I'm going to leave this up for a second because I suggest you probably don't, because I have like a ton of stuff in a half-hour slot, and some of it takes a while to run. It will be up on GitHub. It's actually up on GitHub already. I'm JMX Pearson on there. So this should be up as a repository. You can download the slides. But this is what you would have to do to get it to run. There's one piece I'll tease later if I have time. And that piece should be up in the next couple of days, but is very, very experimental. So I want to do a little bit to set expectations here at the beginning, which is I did the classic speaker thing, which is I gave like this really exciting talk. I'm not a statistician. I'm a neuroscientist, and I tend to think I'm a decent coder for a neuroscientist, at least in languages that Tim Holey doesn't often also like contribute to. So I do this because I want to solve really practical problems. And it's a little bit difficult to sort of design an API for a research program. And that's a little bit what we set out to do with this. So just to tell you a little bit about me, this is my lab at Duke. And we do computational neuroscience. We do some experiments. I've been using Julia for about a year. I really got a lot of start last year watching these same talks from the conference, so thanks for putting them online. And I'm a member of the JuliaStats organization as of the last few months or so, and I've been contributing there. So in my lab, we actually set out to solve a whole bunch of related problems, but this is kind of the one I'll talk about today, which is that we have some behavior and some brain data from some kind of animal. So that can be mice, that can be rats. In our case, it's often monkeys. We actually do get some brain data from human surgery patients. And in that case, we're often getting time series. So this is how I got into using Julia, is I had to write loops for things. And the first day I coded something in Julia, it beat my Python code by a factor of 10, and that was doing all sorts of things wrong, and that was that. So this over on the right is pretty typically what we deal with, which is we have a bunch of spike trains. So it's a point process. That is, neurons make these characteristic electric spikes, and they make them at fixed times, and often we just say, I just want to care about when the neuron spiked. So I may have, in a fairly large experiment now, a couple hundred neurons, and they're going to be spiking at different times. So we might have a point process. The other version of that is we're just taking continuous voltage readings, say, from the surface of the brain. And we have 100 or we have 1,000 channels, and we're getting about 2,000 samples a second. And in our case with surgery patients, they're in the hospital for about 7 days. So if you do the math on that and you figure out you're sort of now in the terabytes range for data, and we would like to actually cram a bunch of subjects in there. So now we're talking about potentially tens of terabytes. So we're in the process of scaling up there, but all of the out-of-core stuff becomes really important for us. It also is kind of interesting statistically. So I think I've already said this. We want to do things that are scalable. I'm at Duke, so I'm kind of contractually required to be at least a little bit Bayesian. So we do this because we want to handle uncertainty correctly. But what I'm going to talk about today really works for all sorts of models. But this is the problem we want to solve, is we're really interested in generative models. Black box models are great if you're just solving an engineering problem. We're often interested in generative models because we have some idea about how the data are generated, and we want to do inferences on the parameters of the models that we think are actually resulting in this brain data. Black box models are great if you want to actually predict the future, but they're not necessarily the best for doing science. If we don't know how the model is fitting the data, then we often don't get as much from it as we want. So the traditional solution to these models is to do Monte Carlo sampling. So I'm a big user of Stan, and not always through the Julia interface, but Bob Carpenter talked about that here last year. I think Stan is a great program. LoRa and Mamba are also packages in the Julia ecosystem that do this and do it well. So why do we want to do anything else? Well, the answer is that sampling does not scale super well. There are tons of people out there working on more efficient samplers, but in general, you say, I have a distribution over the parameters I don't know, and I can't write down what that distribution is, but I can draw 1,000 samples or 10,000 samples from it, and then I can kind of do things with them. I can do statistics with that, and that gives me a sense of what's in my data. Now, unfortunately, we're now usually dealing with parameters where we have 10,000 or 20,000 parameters, and if you run that in Stan, would have been a big model 10 years ago, is going to be on the time scale of several hours, and maybe, I see people on the mailing list, it's a couple of days, and we would like to not wait that long if we don't have to. So there is a way. Some of you remember this old episode of The Simpsons. The package was very nearly max power JL. So Homer says there are 3 ways to do things. There's the right way, the wrong way, and the max power way. And Bart says, isn't that the wrong way? And he says, yes, but faster. That's what variational inference is. It's the wrong way, but it's faster. So the idea goes like this, and this is, I'm one of the few serious equations in the talk. We have a generative model for the data. So theta are going to be my unknown parameters, and y are going to be my data. So in my case, I have a prior here, p of theta. You don't have to. And then I have some model that says, given my thetas, how did I generate the data? So that's a model, and that's our generative model, and we write that down, but we may not know how to sample from that effectively. What we would like is this posterior model, and that's sort of Bayes' rule on the other side. So we would like to know what we can say about the parameters given the data we've observed. Now, what's unfortunate is that p of y over on the right-hand side is something that we usually can't calculate. It's really, really computationally intensive. It's kind of exponentially hard. So we're going to do a cheat. And the cheat actually comes, as many good things in statistics do, from physicists. And so we say we're going to have an approximate posterior distribution, which is called Q, and that's going to be something that we can calculate things with really easily. As we're going to see today, in some cases, this is entirely normal distributions. And then we want to maximize this thing. For those of you from a physics background like me, this is minimum free energy. For those of you from a stats background, we're actually lower bounding the log probability of the data. So this is called the ELBO, or the evidence lower bound. Cut to the chase. The far right-hand side has two terms. You should think of the first term as how good is my model under my approximate posterior. And the second is going to favor less certain models. It's going to smooth my data out. So it's like a regularizer. So for those of you who are used to sort of sparsity penalties or smoothness penalties in other machine learning models, it's going to work like that. So we have this trade-off between goodness of fit and sort of smoothness of the model. That's the thing we want to optimize. We're going to be maximizing, by the way, instead of minimizing. So just so you know how to look at the curves later. So that's it. We've turned a statistical inference problem into an optimization problem. And if it were easy enough to plug into JUMP, which I would love to do, I would go home. But it's a very different kind of optimization problem. So this scales well. We can use all these well-studied techniques. So to the 15 different stochastic gradient descent algorithms out there, I would like to just supply an objective function and a gradient and have them do their thing. What are the drawbacks? I've coded this model or versions of the model 3 or 4 different times. I coded it by hand in Python. I coded all the expectations. It's really the expectations over here that are a killer, right? I'm taking an expectation of some distribution P, which may not be the same as the distribution Q, and often you have to do a lot of algebra to do this. And often, in order to make it fast in languages like Python, you're actually coding expectations of tensors of distributions with other tensors, and it's easy to get turned around on what index goes where. And it's really hard to debug. The only thing that saves you is that if you actually are calculating this function and not approximating it, it's guaranteed to go up. So you have some guarantees, but we're going to get rid of those because we're going to approximate it. So it's really hard to code. And the hard part about that is I want to solve practical problems, and for that, you really want to build a bunch of models. You want to be able to iterate on this. And traditionally, this requires that you do a lot of algebra that is kind of error-prone and tricky. But VB is actually, variational Bayes is actually a technique getting a lot more attention because it's now built into languages like Stan, at least one version of it is. Really, it probably took off because somebody did deep networks with it. And so now everybody's interested. So these are networks that don't just classify your problem, but they will generate new instances. So if you build a recurrent neural network with one of these deep autoencoders, it will let you actually generate samples. So you can produce new kind of fake data and see how well you did. It's a much more sensitive method of checking if your model is correct. So there's a fair bit of stuff out there. So you might say, well, why in the world would you spend all this time making this package? So like I said, this is in Stan, and I think Stan is a great package, and they have a really good development process. It's accessible from Julia, it's accessible from R and Python and all these other things. The variational methods in it are still experimental. I think as of a few weeks ago, you had to do the command line version, and you were fairly locked in, and that's because this is part of their research. So it's great that they're offering it to everyone, but you also have the two-language problem. They develop entirely in C++, and they've built this huge automatic differentiation library, and it's a huge math library, and it's kind of a beast. And I think they've done a really great job of trying to make that accessible, but if you're not a C++ coder, if that's not your daily language, and you don't have that tool chain built, I think it's kind of intimidating. Edward is actually done by, there's some overlap with the Stan team. This is in Python. I think they're actually trying to solve the same problem. They just released this a few weeks ago. So this looks like a great package. It's in Python. That's a pro and a con, depending on how you think about it. It's also very new. So I think this is built as a tool for researchers, which is kind of what I'm targeting too. And then there's Theano and TensorFlow. So people are starting to build variational Bayes methods in these. The difficulty is that they're really just built to do neural networks. If what you want to build is a multi-layer neural network, they're super great, but they're not statistically aware. So all the functions that you would want that are already computed, that are expectations and things like that, are not there, and you're going to code them yourself, and you're going to code them in Python, or you're going to go down to C++ and do it. So you kind of run into this problem of nothing is quite sitting at the intersection of making this set of models easy. So ideally, what would we want? Well, we want something where we can write math and get code. That is, we want something where we have a domain-specific language, something that looks as close to the real math as possible, that's something intuitive for practitioners to write, or at least people who are on the more sophisticated end of practitioners, who are doing research in machine learning. We would like to generalize across indices. I don't want to rewrite my entire code base if all of a sudden I've got an extra variable and I want to index everything by that. We only want to be weakly opinionated about inference. This is a very active area of research, and every few weeks somebody's got a new method for approximating this objective or solving this problem, and I don't want to necessarily be locked into one until the end of time. I really want the model code to be hackable. That is, I would much rather have a set of primitives that we can kind of put together and mix and match in a bunch of ways than one system that is idiot-proof but kind of a closed box, unless you clear a big hurdle. And fast prototyping, minimal algebra. We would like automatic gradients, and I'll talk about that in a little bit. So this is the package. It's really mostly vaporware at the moment. What I'm going to show you today are sort of two use cases that we do have coded, and we have working, they have holes in them, but you should think of this as my kind of commercial to get you interested and convince you that this is a going concern so that you can join my lab in working on it. So I think I've mostly said all of this. I will say this is kind of a consenting adult's philosophy. There's not a ton of error checking. I assume you kind of know what you're doing and you're going to invest a little bit in it if you use it. But I've tried to make it nice. So I'm going to talk about two prototypes today. And the first one is kind of how variational inference started, which is I'm going to deal with models where you can actually do the math in closed form. At least most of it you can. So models that have what's called conjugacy in the statistical literature, which means if my prior takes one form and my likelihood takes another special form, then my posterior distribution I can actually just write down, just by doing a very simple algebraic update. And then in the second case, I'm going to talk about this work by Andrew Gelman and Dave Bly's group at Columbia on black box models where I don't have to have that at all. I can really just fit anything. Whether or not it's a good fit is a different question. So model one, and I'll actually show you some code. So this is the warning, by the way. There's a process I'll talk about that we've been going through with distributions to make it workable for all this. One of those things means that for right now, while we still have a dependency on rstats, I have to overload some methods, some log PDFs that shell out to rstats, and assume that things are float 64. So I've overwritten a couple of things, and you will get these warnings, and they're not going away until rstats goes away. So the idea for the first kind of model actually comes from an old talk that I dug up online from Tawa Lin, which is this idea of a factor graph. So every node in the graph is a distribution. It actually may be like an array of distributions, each one of which, so I have a 4x8 array of normal distributions, which is pretty common to have a bunch of them together. And then factors are terms in that objective function. So they're places where a bunch of nodes come together and I take an expectation and I get a number out. But we're not locked into a graphical model structure. Andrew Gelman loves to say this about Stan, that Stan doesn't have to do with graphical models. You're just defining a function you want to optimize. Same thing is going to be true here at the end of the day, but conceptually this is nice. So I may need to up this a little bit. That should be better. So this is how we would make one of these things. I've just overloaded tilde because statisticians like this. I'm used to looking at this. It'll still work. We'll have to do some things if tilde no longer is a macro, but right now this is just overloaded. And you can see I'm just using the distribution names from distributions. And they're overloaded in such a way that what this macro does is unpack the giant tensors that are on the right-hand side and just apply to all the pairs. So this is just doing a big map. But now on the right-hand side, you can do things like put tensors in, and you can have constants. And notice that I'm being consistent in my use of indices. So all the first three guys have index j. and y there has indices I and j. And that's going to be important because if you're consistent about your indices, all the sums are going to happen in the right way. And that's actually where a lot of this stuff is happening under the hood. And then I would define a factor like this. I have this macro, and the macro says that I want that expectation of the log of a distribution, and these are the 3 nodes that I want to go into it. As of a couple of days ago, I actually have a nicer syntax for this. This @p_model macro will define a log normal factor for you, and it will tell you that the canonical names, x, mu, and tau, are the nodes on the right. Now I'm going to go down. OK. It's pretty easy to define a factor. This is done with another macro. This thing is kind of macros all the way down. This is mostly looks like math. There's this little domain-specific language where E is mean, is overloaded with mean, and V is actually diagonal variance, and C is covariance, and they're overloaded for all the distributions where they make sense. And what this actually does is take those distribution tensors and do the appropriate thing to them. And this guy gets put into a generated function that appropriately sums over all the indices. So what we're really doing is defining kernels here that just get spliced into generated functions. And I've not had to put indices anywhere. There's a projection function that actually rewrites this code to put the appropriate indices in all the appropriate places and deal with inner and outer indices. So if you have a multivariate normal in every one of the rows of your matrix, this knows that the index of that multivariate normal, well, I'll just show you an example. So the models are just factor graphs. So if we wanted to do the following model where we say this is the model that generated the data, I have some data that are generated from a normal distribution with mean mu and precision tau, which is the inverse of the variance. And tau is from a gamma distribution and mu is from a normal. And I want to approximate it by a normal distribution on mu and a gamma distribution on tau. So for those of you who are in the know, this actually is a conjugate model. You can solve this exactly. And in fact, this is how it would look. So I'm going to define those nodes up at the top. These are my posterior approximation. And so I've got some consts that are up here. And that may be a little simpler to do in future and may go away. But I'm essentially saying I want my approximation to have this form, and my generative model has this form. And now in my model, here are all the nodes, and here are all the factors. And it turns out that if you ask the package what the update strategy is, it knows these nodes are constant and these nodes are conjugate. And it does that by looking at all the conjugacy relations that I've defined, and then you just call update on M. And in this case, what it does is Bayesian updating. And so it's a one-step solve. But in cases where this is not true, right now it defaults to a brute force optimization on non-conjugate things, BFGS or conjugate gradient or something like that, and you would do a step of that and you'd iterate. For conjugacy, there's another macro that essentially says if I have this factor and this node is approximated in this way, then these are the sufficient statistics. These are the things I have to know about the distribution. And again, you write them in this little math-like syntax, and then it handles all the indices for you. That's just more about index bookkeeping and a little more about indices. I'm going to skip to get to my second point. This is a very different kind of model. And I think it's an open question how to get these models to talk to each other in an appropriate way. So if I have a bunch of nodes that are fast to update in a conjugate way, how do I combine that with models where I use something like automatic differentiation, variational inference, to do the non-conjugate stuff? The idea behind this is pretty simple, but actually pretty great, which is that we just need to define that objective function or an approximation to it. And the other approximation, which I think, again, it's a research question how well you can do, is that any distribution with kind of one bump, if you transform it to be positive or a covariance matrix or whatever, is basically a Gaussian. That if you go to the space where the variables are unconstrained, you can put a Gaussian on it and do OK. And I'll say as somebody who's like really doing this for biology, where the noise floor is enormous, it's probably pretty good for me. So this is what they do. You're going to approximate this function by sampling all the parameters from a normal distribution and then constraining them appropriately. So if it's a gamma and it has to be positive, you take a sample from the normal and you take the exponential of it. And there are more complicated transformations, and they've got a whole bunch of them. Then you let your autodiff library do all the work. You defined your objective function, do gradient descent on it, and go home. Actually, gradient ascent in this case. And we have autodiff. This is actually one of the great things about working in Julia is the Stan math library is kind of enormous, and they had to build an autodiff library, and they had to build a distributions library, and they had to do all of it in C++. I don't have to do any of it because we have an autodiff library, we have a distributions library that has like fast immutable types for all of these things, and we just want to put them together. So in some sense, all I've written is a nice package to like build objective functions. But there's always a problem. And the problem is that if you want to use a really great package like forward diff, that defines a number type that's a subtype of real, and you should be able to plug that into all your functions, and it takes all your derivatives automatically. Except that everything in the distributions package assumes that things are ints and floats. And it's baked in so deeply and is so ubiquitous that it's been a lot of surgical operation to get this done. This started off with parameterizing the normal distribution so that mu and sigma could be any subtype of real, and I did that a few months ago. There's been a lot of work. This is why I told you to check out that branch of distributions. Today, PDMats is fully parametric in the element type. So if you're using positive definite matrix, you can stick a rational in that thing. You can stick ints, and it'll do all the right things. And it'll work for you, and you can dispatch on that. Everything that uses a PDMat, so all the multivariate normals and the t-distributions and the Wisharts, those all work. You can differentiate functions of those now with forward diff, and it just works. There are a handful of others I've done to make this stuff work today, and there are examples. I've got a whole repository of tests for these things to show you that they do what they're supposed to. What's more important than that is I've got a student in my lab who's working on a giant PR, and I think within the next month we're going to have about 40 distributions in all the univariates, and I think in probably the next 2 months the distributions package will be fully parametric in the input arguments, which means any function using those types will now be differentiable with forward diff. So that's a lot of where the work is gone. There are some special functions in stats funds and base that still need to be fixed, that before they finally go out to some C library should probably take a fork in the road if they get an autodiff variable. But that's fairly small. So here's my simple model. This is inspired by my neural example, and I'm going to go backward. I have a whole bunch of counts, spike counts, that are distributed as a Poisson, and I'm going to assume it's log normal. I just read that as log normal. This guy is a normal distribution, and every unit, I assume, has a normal prior, and there's some noise around it. So what I say is I have a bunch of neurons. They have baseline firing rates. I know something about what that is, but they're all kind of different. And then on every single time, in every single time bin, there's some little noise around that baseline firing rate. So the data for this, I'll show you the data after this. This is how I do the model in ADVI. And those of you who are used to using JAGs and bugs and stan, this will look very familiar. I have a macro up here, and I'm going to declare these. A is a real, and there's a vector of u of them. Sigma is a positive. Eta is a real, and it's a t by u array. So I'm really just telling ADVI what type of variable it is. What are the constraints on it? And these can be things like it's a simplex, it's got a sum to 1, yada, yada. And then I have an ADVI model macro, and this just says, oh, well, here's my model. A is normal, sigma is gamma, eta is normal, and my data are actually distributed as this. So you write it just the way you normally would. We could vectorize this later, but for right now, you do loops. And all this does is write an objective function that then gets compiled. So if you do macro expand on this, all this does is set a counter, and it kind of unrolls your x vector, builds all these distributions, handles all the sampling, and what comes out of this whole thing is you've got a function that you can then go optimize, and you can take an automatic gradient of. So the data look like this. These are my 10 units, and these are my 100 time steps, and the heat map just sort of says what was my count in each bin. This is just my parameter counts, and I'm doing some math here to figure that out, and I can calculate. And sorry, this is cut off the top. There we go. So I'm doing my storage bit here, and I can time this, and for something that's kind of moderately sized for about 2,000 parameters, I can do about 1.5 seconds. So enough that I can clip along on a smallish model and do what I need to do, and there's my gradient. And then this is why I would prefer to use somebody else's SGD, as I don't do this for a living, but I'm essentially doing some gradient clipping in here and some RMS prop, and I run it for like 160 iterations, and it looks something like this. So we get some convergence, and we get back what we would expect. So that's ADVI, and it kind of works. I don't have all the types defined, but the machinery is all there. So it's fairly easy to build out and does what it's supposed to do. The trick is that this was 2,000 parameters. It takes a few minutes to fit, but that's not big anymore. You could plug that into Stan, and I think it would chew through it probably faster. So this is my teaser, and I've talked to a couple of people about this, but this is what I've been hacking on like late last night and a little bit earlier in the week. So those of you who were at Miles's talk and Jarrett's talk, you know that like forward mode auto diff, which is the one that's really easy for us to use in Julia, is really bad. This is the reason you don't hear much about it, is because for the functions that we want to optimize, which take a gajillion inputs and have one output, we have to evaluate this function basically n times. And n is like, you know, what, 5 million or 6 million for the expression graphs in these deep neural networks. It just doesn't work. If you want to do reverse mode, also called backpropagation, that's order 1. You evaluate the function once forward to set it up and once backward, and then you're done. But reverse mode is really hard because you have to keep all this stuff around in memory. So once distributions are parametric, though, there are some things you can do. So there is an idea that if you make the right kind of number that keeps track of this, and other libraries do this, the AutoGrad library in Python that somebody mentioned the other day, you sort of record this tape. You send a variable type through, and it kind of records in some other variable somewhere on a stack, like everything that happens to it, and then you either generate code, and you write that code on the way back, or you just build up a giant stack, and then you run it backward to convert your backprop. You can do it, and you can do it by just subtyping real. And this is where it becomes really powerful to work in Julia, because I implemented this. I did the arithmetic operations, comparison, convert, and promote. And all of a sudden, I could differentiate this. Like, I will show you guys code later for those of you who are interested afterward, but it's really like 30 lines of code, and I can now differentiate that objective function in reverse mode. The memory usage is terrible. The optimization Stefan talked about this morning about being able to stack allocate things that refer to the heap is going to help us a ton. But this is the time comparison. So this is for, I think, 20,000 parameters. This is forward, and this is reverse. There's a huge speed up. And this is a lot of hackery, but it's really promising. And I will tell you that if you generalize this to allowing yourself to take shortcuts when things are already in arrays, you get another couple of orders of magnitude speed up. I pushed it today. I had 20 million parameters, and I was able to do a differentiation in 2 seconds. So there's a lot of work to be done with this, but I know that some people are interested, and I'm hoping to talk to those of you guys who are. So that's my commercial. This is still very much a work in progress, but I hope over the next so many months, as my lab works on it, it becomes a more usable tool for you guys. And so please come see me if you're interested, or if you have better ideas. I'd love to hear them, and thanks.